Hello, and welcome to the Chapter 16.3 lecture on polar coordinates. So, recall from the end of Calculus 2 that polar coordinates are another way of expressing points in R2. So in the Cartesian coordinate plane, you have a coordinate a comma b that gives the x and y coordinates of the point. Well, in the polar coordinate system, instead of the x and y coordinates being the ingredients, we have the radius r, its distance away from the origin, and then the angle theta that the point makes with the x-axis. So polar coordinates are in the form r comma theta. And unlike Cartesian coordinates, points in polar coordinates do not have unique coordinates due to the cyclicity of theta. Namely, if you go around 2 pi, you're back to where you started. So every point has infinitely many polar coordinates. So for example, this is the point negative root 2 over 2 comma root 2 over 2 in Cartesian coordinates. And in polar coordinates, we can express that point in a number of ways, one of which would be 1 comma 3 pi over 4, because notice that the radius r here of this, that would be r is the square root of the sum of the squares of the x and y components by trigonometry, and that is 1. So that is why the radius here is 1. It's 1 away from the origin, and then the angle it makes is 3 pi over 4. However, we could also think of that same point in the following way. We can think of a radius of negative 1 facing in the direction negative pi over 4, which is this way. However, if your radius is negative 1 and you're facing in a direction, that means that you're facing in the opposite direction. So just like how given a vector v that might be facing this way, then negative v would be facing in the opposite direction. It's the same way as that. So negative 1 comma negative pi over 4 gets us to the same point. And then these other two illustrate that if we add 2 pi, then we just make a full cycle and we get back to where we began. Okay, but while there are all these ways of getting to the same point, we typically will just give the polar coordinates with a positive r and theta between 0 and 2 pi, and we won't really have to worry about this. Okay, now we'll be wanting to convert between Cartesian and polar coordinates. So first, the radius r to a point, that's the hypotenuse of the triangle with sides x and y, where x and y are the Cartesian coordinates. So r squared is x squared plus y squared. And also the opposite over adjacent, that's the tangent of theta, so tan theta is y over x. So that's a nice way of getting r and theta from the Cartesian coordinates. And going backwards, if we're given r and theta, then by trigonometry, x is r cosine theta and y is r sine theta. So these two are our conversions back and forth. So for example, let's convert root 3, 1 to polar coordinates. Okay, well, r would be the square root of root 3 squared plus 1 squared, which is 2. Okay, and technically it could be negative as well. We're just going to go with the polar coordinate with r positive and theta between 0 and 2 pi, a polar coordinate for it. Okay, and theta would be the arctangent of y over x, that's 1 over root 3, and that is pi over 6. So a polar coordinate expression for that point in Cartesian coordinates is 2 comma pi over 6. And we'll sometimes want to express equations in polar coordinates. But where we're going with this is re-expressing bounds of regions R in polar coordinates, which is something that will make a number of double integrals much easier to do. And to do things like that, we want to convert Cartesian bounds to polar bounds. So how do we do that? Well, x is r cosine theta and y is r sine theta. So we just do that substitution. and this is r sine theta is r cosine theta squared. So we have this, and if we wanted to express r as a function of theta, we would solve for r, and we would get r is sine theta over cosine squared theta, and we could re-express that if we wanted as r is secant theta tan theta. Now we'll often want to do double integrals over disks with bound like x squared plus y squared is 1. So how would you express this in polar coordinates? So as we go forward in this class, we'll always want to keep our eyes out for bounds of this form or instances of this form in general, because x squared plus y squared is r squared. So that's simply r squared is 1 or r equals 1. Ignoring the negative r, which we can always do in practice. And the point is that if we have a bound like this, then in Cartesian coordinates, we would need to solve for y, and we would have a square root of 1 minus x squared. While in polar coordinates, we just have r equals 1, and it will be so much easier to integrate with a bound like this versus a bound like square root of 1 minus x squared. Okay, so what polar coordinates do is they will convert regions that would have square roots of 1 minus pieces squared to rectangles. And I know these don't look like rectangles, but they are rectangles in polar coordinates in the sense that they have constant r bounds and constant theta bounds. So this region r here is in polar coordinates all r between a and b, the difference in radii, and all theta between alpha and beta, the difference in angle. So it's not hard to see that this would be a rectangle in polar coordinates in the sense of constant bounds on r and theta, but these two are also, quote, rectangles in polar coordinates in the sense of constant bounds on r and theta. Okay, so again, the idea is that to integrate over a region r that looks like this, it will be much easier to do it in polar coordinates, because then from here, we would have an integral like 0 to b and 0 to pi over 2, nice constant bounds of something dr d theta. And those constant bounds make it much, much nicer to integrate, whatever that function will be. To do so, though, we'll also need to re-express our surface in terms of polar coordinates. So let's say that we wanted to find the volume underneath this paraboloid, z equals 9 minus x squared minus y squared, over the disk x squared plus y squared is less than or equal to 9, which is its intersection with the xy plane. As you can see by setting z equal to 0 here, and you'll get that it's a circle of radius 3. And in this, because x squared plus y squared is r squared, then 9 minus x squared minus y squared, which is 9 minus parentheses x squared plus y squared, has a nice radial expression as 9 minus r squared. So we might think, okay, well, I'll just integrate 9 minus r squared over the region with bounds of r between 0 and 3, and theta between 0 and 2 pi, making one full revolution. Okay, nice idea. That is the gist of it, but there is one little caveat that is very important. A slight modification of the double integral when we convert to polar coordinates. And it stems from the following. In Cartesian coordinates, the various rectangles in a regular grid would all have the same areas in the Riemann sum. However, if we make a regular grid in polar coordinates, then the areas of these rectangles are increasing as r increases, as you can see. That area is less than that area, even though they both have the same delta r and delta theta. And recall that the area of a sector of a circle of radius r subtended by an angle theta is 1/2 r squared theta. And you can get this by that the full area of a circle is pi r squared. You can think of this as 1/2 times 2 pi times r squared. And that's 1/2 times theta times r squared for any theta that's less than 2 pi. Okay, now what we're going to do to find this little area of the base of our rectangular solid in the Riemann sum is take the differential. So that'd be del del theta of del del r of 1/2 r squared theta. And if you compute that, then, okay, del del r is r theta, and del del theta of that is just r. So then multiplying both sides by our del theta del r and expressing it as dr d theta, we have that the little base there is r d theta dr. So in other words, the base times height of the rectangular sliver will be the height, whatever that function is, times the base, and we'll be adding together all of these in our Riemann sum. So in other words, this is our dA, and that dA is not just dr d theta, it is r times dr d theta. So the point is, when we're integrating in polar coordinates, always add this r right here in red. So here's the theorem for how to express a double integral in polar coordinates. So given a function f of xy that we want to integrate over a region R, where that region R is a rectangle in polar coordinates, so it looks like one of these. Okay, so we need to convert everything to polar. So x is our cosine theta, y is our sine theta, so we just need to do those substitutions in the function. And then we add that r right there. That is from what we got here. So don't forget to add that, because this whole thing is that dA. And then dr d theta between the r bounds and the theta bounds, whatever they may be. So let's do this example to illustrate this. Okay, so our region R here, that's the set of all x squared plus y squared is less than or equal to 3 squared, which is r squared is less than or equal to 3 squared, i.e. r is less than or equal to 3. So we can express this circle as r is between 0 and 3. And what are our bounds on theta? Well, theta can vary between 0 and 2 pi, and that will give us everything. Theta is between 0 and 2 pi, and we can stretch between the origin r equals 0 out to r equals 3. Okay, so the double integral over this region R of 9 minus x squared minus y squared dA, that will be the integral of 9 minus, okay, so remember that this guy, that's the same as minus r squared, and we need to convert our function z to be in terms of theta and r. So that's 9 minus r squared. And then don't forget to add that r that we always have to add when we do it in polar coordinates. And we'll integrate dr d theta with the appropriate bounds. R varies between 0 and 3 in this case, and theta goes between 0 and 2 pi. And by Fubini's theorem, because these are constant bounds, you can actually swap these and swap the d theta dr if you wanted to. In this case, it really doesn't matter though. Okay, and contrast with what it would be if we had tried to do it in Cartesian coordinates. We would have bounds, as at the end of the previous lecture, of negative square root of 1 minus x squared, positive square root of 1 minus x squared up here, and it would not be fun. But this is very elegant. It's just constant bound integral of a polynomial, and not bad at all. So we got this. We didn't forget that r right there. Distributing that r inside and taking the integral, we have this. It's just the integral of a polynomial. We evaluate that between 0 and 3. And then we evaluate that between 0 and 2 pi. And we get that the volume here is 81 pi over 2. So that's integration in polar coordinates. And whenever you see an integral over a circular region, then really you want to do it in polar coordinates, because the circular region has nice constant bounds in polar coordinates. And just never forget that r. I can't emphasize that enough. So many people forget it. So go ahead and try your hand. Find the volume above the depicted annulus. This shape here is called an annulus, and below the paraboloid z equals 16 minus x squared minus y squared. I encourage you to pause the video. Okay, so we're taking the double integral of 16 minus x squared plus y squared in parentheses dA over this region. And we definitely don't want to do this in Cartesian. We'll have square roots of squares all over the place here and have to break it up into different parts. But in polar, this is very nice. We're moving from r equals 2 to r equals 4, and theta between 0 and 2 pi. Okay, so r goes between 2 and 4, theta goes between 0 and 2 pi of 16 minus, so we need to convert our z to polar, but x squared plus y squared is r squared. Now, don't forget that r, as always, dr d theta. And from here, it's a direct double integral. We distribute the r and integrate and get this. Evaluating that between 4 and 2, we get 36. And that between 0 and 2 pi, the integral, we get 72 pi. Okay, and so far these have been polar coordinates in which our double integral bounds have been constant, but we can also have variable bounds in polar coordinates. So for example, say we wanted to integrate z equals x squared plus y squared over the depicted region here. Okay, so first we would need to find our bounds on theta. They tell it to us in this picture, but we could also solve for these bounds on theta by finding the intersection of 4 cosine theta and r equals 2. So in other words, we have r equals 2 and r equals 4 cosine theta. What is that theta? Well, we set those equal to each other. We have 2 is 4 times cosine of theta. That would mean that cosine of theta is 1/2. And that would mean that theta is plus or minus pi over 3. So that's where these bounds on theta came from. And our r is moving from r equals 2 to r equals 4 cosine theta. So the double integral over r of x squared plus y squared dA is, okay, let's do dr first, and then d theta. Never forget that r right there. This guy here is just r squared. Okay, and our r is going between 2 and 4 cosine theta. And then our theta is moving between pi, negative pi over 3 up to pi over 3. So that would be our setup to find the double integral of this function over this region. Okay, so it would come down to evaluating this double integral. And that's really a calculus 2 exercise. The important part is the setup. Now, one final and important note that we'll be using a lot actually is that we can find areas with rectangular and polar coordinates slickly in the following way with double integrals. Note that if the surface above your region R is of constant height 1, then the volume of that surface would be the base times height, which is the base times 1, which would just be the base. So in other words, if you take the double integral of 1 over your region R, and we typically just omit the 1, and that would be the double integral over R of dA, then what you get is just the area of R. Because then the base times height is just the base, and that base is the area of R. So for example, if we wanted to find the area of R here, all we would do is take the double integral over R of dA, and we would have those same bounds that we got before, except now we would plug in z equals 1 to find the area of R and evaluate that double integral. So that concludes this section on polar coordinates and integration in polar coordinates. Have a great one.